title says, it's a bit old-fashioned with many words, statistical physics. Well, statistical physics is a large area, so I will speak of statistical physics of lattice model of natural phenomena. So usually we say statistical physics of a lattice model, but it's model, you can't have a model, it's always a model of something. So it's model of something which occurs in nature. And I will mostly speak about things which happen in two dimensions, which is fairly natural. There are two-dimensional things in nature, like the recently discovered two-dimensional materials, but also there are phenomena which happen on the surface of water, or surface of Earth, and a little bit touch in the beginning of dimension 1 and dimension 3 at the end. And the dates are, well, I'll explain later why those dates I have chosen. So what is statistical physics? Well, statistical physics, it's a science which studies macroscopic effects of microscopic interactions. So, for example, what you see here on the left is erosion. Well, it's a computer model. You can also film erosion over a mountain, but then you have to run it like for 50,000 years to see an interesting phenomenon. But what you see that we start with shapes which look very different, which are smooth or irregular, but then erosion, erodes them to similarly looking fractal shapes. Actually, fractal dimensions for thirds, it's now a theorem of the boundary, and it was a conjecture by Benoit Mandelbrot. And here what happens is that the local phenomenology is very easy. You have an individual grain of sand which is attached, and then it's sort of pushed on by wind and water and other elements, and then maybe it will come loose, maybe not. And then if it comes loose, the next is up for being influenced by the elements. Or on the right, but you see a global picture, not the individual ones, and the global becomes much more complicated. On the right there is a picture of a DNA made by atomic force microscopy, and essentially it's a molecule which is a long chain, a polymer molecule, and normally it's in a very knotted state, but at certain periods of our lives we have to unknot them to replicate, and again it occupies some very fractal position. Actually, if you do two-dimensional analog, again it will be the same curve which you see here after some erosion. It's again a fractal curve for dimension 4/3. So I will speak, but you can see a complicated shape, but it's all decided by a chain where there is some local forces which say something about next links, how flexible it is, and so on. Basically what statistical physics does is proposes mathematical models of such natural phenomena where there is a simple macroscopic interaction, but you see a very complicated macroscopic behavior, and then you try to explain it. Ironically, it was suggested by ancient Greek philosophers that this, who propagate the idea of atomism, that this might be reasoned by some complicated phase transitions we see in nature. They actually propose that boiling of the water boils down to some microscopic effects, that individual atoms, they just move faster and faster in a continuous sort of way. But then bumps at temperature 100 degrees centigrade, they move too fast, and their force combined leads to a phase transition. Of course, at this time, 2,500 years ago, it was just purely philosophical exercise. But what is really happened, really about 100 years ago, we started again explaining such phenomena as boiling of the water from the mathematical point of view, where complicated behavior at the scale we observe boils down to very simple behavior at the scale of 1 atom, but added for millions of atoms of water in one glass. So the first really mathematical theorem which has similar explanation is the famous one of, so Einstein wrote 3 famous papers in 1905, and one of them, it was related a bit to the heat transfer, based on an earlier work of Fourier, but now building a real mathematical basis and relating it to motion of individual molecules, or rather motion of vibration of individual molecules. And he had a really scientific application to Brownian motion, which built a mathematical model for the Brownian motion. Well, the real mathematical model was built by Wiener some 20 years later, but he built a sort of semi-discrete model, and he showed that it can be successfully applied, and it has several parameters, and these parameters can be calculated in nature using experiments. But then you make some deduction about other parameters, and again they can be observed in nature. And this paper essentially was the first scientific theory, well, the first scientific argument towards the atomism, towards the matter indeed is constructed of atoms. So we will discuss not this model, this model random walk Brownian no motion is very well understood nowadays. We will discuss a model which often it's said in physics book that it's equally well understood, but where the research is still ongoing, and this is a model of magnetism. Magnetism, people again knew for like about 3,000 years, and the name magnet, it comes from a name of a province in Greece which is rich in iron ore, and there was some semi-scientific discussion in ancient Indian text or ancient Greek text, and it had some practical uses. The most famous one, of course, is the needle of a compass, but it was also used in India in surgery by sort of pushing needle through. So people applied it practically, but was very poor understanding of its nature. It just was known that certain iron-looking materials are magnets, certain are not. You can magnetize other materials sometimes, but they are not as strong. And people mused about this, but for hundreds of years without much success. And the first breakthrough, it came by accident at a Physics 101 lecture in a Danish university by Hans Christian Ørsted, who otherwise maybe would have been forgotten by now. So he had some leftovers from a previous lecture, and he ran electric current through a coil, and suddenly needles which were on the table started being attracted to it. So he stayed after the lecture, and he discovered that if you run electric current through some wire, then it generates a magnetic field. So he published a paper, and immediately people started measuring this field and wrote formula for it. So very famous people got involved, so Ampere and Gauss. Finally, the exact formula was given by Jean-Baptiste Biot and Félix Savart. So this is a picture which you usually see in a physics textbook, that if you have a sort of circular wire, then there is this magnetic field which curves around it. So it's a field which is a so-called harmonic vector field. So locally this field is divergence-free and curve-free. So it's locally a gradient of some harmonic function. But its singularity, usually when we deal with PDE, we are accustomed that solutions to different PDEs have point singularities, like Cauchy kernel or Riemann kernel or Hilbert kernel, whatever, like 1 over z logarithm of r. So here, if you study harmonic vector fields, that is vector fields with zero curl and zero divergence, or if you wish one forms which are closed and co-closed, then there are two fundamental solutions. And one is the magnetic field of a monopole. So this is really honest field with point singularity. But the other is a Biot-Savart field generated by a current, through electric current. And its singularity is not a point, but some closed curve. So this is one of the reasons why some theorems in analysis in dimensions 3 and higher are much more complicated than in dimension 2, where you can only come up with point singularities. But it's not a subject of our talk. The next discovery came by Faraday, and that was not on accident, but rather by design. And he discovered that there is a duality, that if you change magnetic flux, it generates electric current. So it became clear that electric and magnetic field, they are actually intimately related, and that led to a series of work Maxwell, and then him writing a book which is possibly one of the greatest scientific books of all times, which combines electricity, magnetism, and light, and has Maxwell's equations, and led eventually to the relativity theory. But it did not, it explained how magnetic field of a magnet looks like, how it's related to electricity, but it didn't explain the physical reasons for why some materials are magnets and some are not. The first sort of, again, the next breakthrough came experimentally. It was a thesis of a famous physicist, Pierre Curie, who never returned to this question. And what he did, he observed that actually there is a very much like water boiling, there is a phase transition in magnets, that all metals are magnetic at low temperatures, but, well, most metals are magnetic at low temperature, but not magnetic at high temperatures. And there is a phase transition. It's not that they lose their properties continuously, but at one point, snap, they stop being magnetic. So if you went to Physics 101 old-fashioned way, you would have seen experiments that with iron, the critical temperature is about 1043 degrees Kelvin grade, so 700 degrees Celsius, so you need a plasma torch to make this experiment. There are materials where this Curie temperature, when they start being magnets, is the room temperature. So I brought a couple of neodymium magnets. So this is basically the strongest magnetic material known today. So this is one of the rare earth metals, and I think it's Panasonic Corporation developed this about like 40 years ago. So there are some alloys with iron and copper, and this is which are basically the strongest magnets known today. So they have a critical temperature about I think 100 degrees. So I can actually try this trick unless I burn my fingers. Just hold it like that so that I don't burn my fingers. I always wanted to perform an experiment at a lecture. Actually, last time I did it, I burned my fingers first. Yeah, actually it's already getting hot even for plastic. Yeah, it's better to do it with a staple, but I don't have a staple. Well, it worked. Yeah. The smell of burnt napalm in the morning. Yeah, so this is the magnets which they use in hard drives nowadays, or which they use if you have magnetic clip in your bag or on your purse, and they're really strong. If you wish to see how strong, just give me your credit card, I will rub on it, and it will sort of be wiped completely. But if you have, for this size, if you have like 2 millimeters in between, it's fairly safe. So it's why they use it in the bags. So what Curie discovered, that there is phase transition, and he again concluded to suggest that it might be something going at an atomic scale which leads to the phase transition. And actually one should say that at that year most physicists didn't believe in atomism. About 1/3 did. So really there is a breakthrough which came around like 1905 with the paper of Einstein and like black body radiation papers. So there were several papers which gave proofs, but they all came in the early 20th century. But anyway, Curie never returned to this, and he more famously studied other subjects. And the first person who proposed the real model was Wilhelm Lenz. This is the model I will speak about. So it should be called Lenz-Ising model, but it's called commonly Ising model, and there is a running joke that models in statistical physics are named after students. So if you find a good model, you give it as a PhD thesis topic, and then it's named after your student. So Lenz model is named after Ising, who was his student, and Potts model is named after Potts, who was student of Cyril Domp, and FK model, well, there are about 7 examples. Here's the reasoning from his paper, and he says that we have a piece of iron or some other ferromagnetic material, and the atoms, small atoms, are like dipoles which can occupy 2 positions, up and down. And then he kind of muses a bit about why they are like small magnets. His reasoning is not entirely correct. He says, well, there is an electron, so it must be a magnet. So probably what he means that it's still early age of quantum mechanics. We didn't know how electrons move around. So actually the pudding model of Thomson was maybe more common these days. But some people thought that electrons would orbit like planets around the nucleus. And then, of course, it's like a very small electric current running around, so it will generate a Biot-Savart field. So each individual atom would be a small magnet, and then the small magnets, they try to align in the same position. Well, again, that's not really clear why in the same, but for example, if they point up or down, they will try north will be attracted to south, south to north. And then he muses that there are 2 things. That first, they cannot occupy any position because it's a rigid crystal, but on the other hand, so they shouldn't be able to change their position. On the other hand, we observe that you can magnetize in one direction and another, so maybe they can flip over. And then they can flip over, and then we say just that the higher is the temperature, the less is the connection between the next ones to each other. So if there is a low temperature, they all try to align the same, and you get all atoms aligned in the same direction, and their magnetic fields add up, and you get a magnet. If there is high temperature, then the thermal fluctuations destroy it. So some are aligned up, some are aligned down, they cancel each other's magnetic field, and it's not magnetized. So this is the reasoning, and it's an early age of quantum mechanics, I mean, what one can say now, well, it's backward side, it's very clear. I mean, first, there is a theorem which says that before quantum mechanics we could not have had magnetism. So if you have a classical solid without quantum mechanical properties of atoms, you won't observe phase transition in ferromagnetism. So we had to wait till early 20th century to find an explanation. And the second is that by far and large the Lenz explanation is correct. But he arrived at it for wrong reasons. So the actual reasons why we have this is why atoms are small magnets, is that electron is a fermion and it has an intrinsic property of having a dipole moment. And this is about 100 times stronger than the one which it generates rotating around the nucleus. So this is the actual reasons why you have these small magnets. And then the second thing is another quantum phenomenon, the Pauli exclusion principle, which says that, roughly speaking, that electrons can't occupy the same position. And then you try to calculate for two nearby atoms their orbits overlap, which configuration is more energetically efficient, when they have the same spins or the different ones. And it turns when they have the same spins, they sort of overlap less, so it's more energetically efficient. So I won't go more into physics. I maybe just comment that there are several different reasons for magnetism in real world. So for example, there are materials where you would have optimal arrangement is checkerboard, and then to the first order the magnetic fields they cancel out, but there are small reminders which add up. Well, so there is ferromagnetism, antiferromagnetism, so there are different mechanisms. To the best of my knowledge, actually the Ising model literally doesn't correspond to any actual magnet, but it very well models the actual magnets, and also it models very accurately ferroelectricity in several materials, word by word. So, so this is, well, that was the model, and Ising used completely wrong logic, but the right logic also would lead to the same model. He gave it to his student, Lenz gave it to his student Ising, and Ising exactly wrote the model. So we need to write what is the effect of the temperature. So he wrote basically this model. So let's suppose we have a two-dimensional crystal, which is a square lattice shape. So we have squares of two colors which correspond to plus spins and minus spins. And nearby spins want to be, so usually people denote them not by colors but by numbers plus and minus 1. And nearby spins want to be the same with parameter x, which corresponds to the temperature. So weight of a configuration is x to the power number of neighbors which are of opposite color. So for example, these two neighbors are red and blue, so you get 1 to the power here. So actually this red square has 4 blue neighbors, so you get 4 into the power. Or for example, the whole perimeter of this red cluster, each step adds you 1 here. So the more you have neighbors which are of different colors, the higher is the power. The higher is the power. And if x is smaller than 1, then the higher is the power, the smaller is the weight of a configuration. Now, it's not the probability of configuration because sum of weights is not 1, so we have to normalize it by sum of the weights. So this is what is called partition function, you sum over all possible coverings, weight of configuration, and then probability of configuration is its weight over partition function. So if you haven't seen this, is it clear? So it's a very easy discrete probability. Now in most countries, well, certainly in France and Russia, they teach it in 9th grade, the discrete probability. So it's very easy. It's a probability space which for a like 20 by 30 square, which has 600 small squares, it has 2 to the power 600 possible coverings. Each of them has a weight, and partition function sum of weights and probability is this thing. So if you open textbook on physics, like Feynman, Landau, Lifshitz, usually they write it with plus minus spins instead. Usually write it not x to the power number of neighbors, but exponent of minus beta sum of over all power pairs of neighbors u and v, spin of u times spin of v. So if spins are the same, you get here number 1 and you get exponent of minus beta. If spins are different, you get here minus. So minus times minus gives plus, you get exponent plus beta. So there are two possibilities. Two nearby spins are either different, then you get exponent minus exponent plus beta, or the same, you get exponent minus beta. And in the first treatment, if they are different, you get x. If they are the same, you get 1. So essentially just a change of parameter. X goes to exponent of twice beta. And x of beta per row of temperature, the actual temperature is the reciprocal of beta. So in terms of x, it's reciprocal of logarithm of x. So if we have an exterior magnetic field, there are two ways to define it. One way you say that it only affects some boundary. So you just say that boundary conditions, for example, are all red. Another way you just say that it affects everything. So you then multiply this by something which tends to push spins towards plus 1 or minus 1. So this is not really important or interesting phenomenology you can already observe with this function without magnetic field, so I will stick with it because it's easier, and maybe I will just replicate the argument of Ising. And what Ising did in his thesis and why the model is called the Ising model is he proved that in dimension 1 there is no phase transition. So so in the first part of my talk I will speak more about what happened to like 60s or 70s, and most of it is either unrigorous physics or rigorous combinatorics. So this is a very rigorous combinatorics argument which says that suppose we have a one-dimensional chain of spins, plus and minus spins, of length n plus 1 in integer. And suppose we know that the leftmost spin is fixed, it is plus. What is the probability that the rightmost spin is plus? What is the probability that this magnetic field from the left end of the rod propagates to the right end? So first we need to compute partition function. We need to compute partition function of all the configurations. If the leftmost spin is fixed and there are n more spins, how many different configurations we have? If there are n spins, how many configurations?
2 to the power n.
2 to the power n. And each time when we change spin from plus to minus, going left to right, we get a factor of x. And each time when we don't change, we get a factor of 1. So essentially, we can take binomial 1 plus x to the power n. And when we open the brackets, we get 2 to the power n terms. And they correspond to individual configurations. So how you construct a configuration if you have a term 1 times 1 times 1 times x times 1. First 3 steps you keep your cover, next 2 steps you change your cover because there is x, and next step you again keep your cover. So basically, for every term in binomial, there is a configuration here. So this is very easy. Now, what does it mean that the leftmost spin, rightmost spin is also plus like the leftmost? It means that we changed our cover how many times? If it was plus and it's again plus, then we flip the cover.
Odd numbers.
Even numbers. So we need to get from partition function the terms where power of x is even. And there is a usual combinatorial trick to do that. You take binomial with a minus sign, and the difference between binomial with plus sign and minus sign is that odd powers here will come with minus sign, and here with plus. So if you add these two binomials, odd powers will cancel out, even powers will remain, but each of them will be twice there, because for this one and that one. So we divide by 2. So this is the whole partition function, and this is part of partition function corresponding to configuration with 2 pluses at 2 ends. So probability to have plus at the right hand side is z plus over z. So we divide this by that. First terms they divide to give us 1/2. The two second terms, second term divided by 1 plus 6 to the power n gives 1/2 of 1 minus 6 or 1 plus 6 to the power n. Now, what happens if you have any number x, 1 minus 6 over 1 plus x is smaller than 1. So if you have a very long chain, this number decays exponentially fast. So essentially, probability to have plus at the right-hand side will be 1/2. So there is no influence of the left thing. So this is not exactly like what Ising did, so this is an easy combinatorial explanation. So what he did, he actually observed that we start with the left square, where we have plus with probability 1 and minus with probability 0. And then there is a transfer matrix which gives you the value of probabilities at the next step by multiplying 1, 0 by 1x, x1, y1x, x1. Because when you change spin, when you are on diagonal, you don't change spin. So you multiply by 1. When you are on the diagonal, you change spin, you multiply by x. So if you want to get what you have at step n, you multiply this matrix n times by 1, 0, and you exactly get z plus and z minus as a vector. So basically the identity would be that this is z plus, z minus vector. And essentially what you need to do to get z plus, z minus, you need to analyze what happens with the nth power of a matrix. So you need just to calculate two eigenvalues. Two eigenvalues for this matrix are not equal. So essentially the largest eigenvalue will attract very fast, exponentially fast what happens. Now if you have magnetic field, well that's a good problem. How do we change this if you have a magnetic field? So suppose there is a magnetic field which adds a factor y, factor y each time when we have a plus spin. So how do we change this matrix then? So one should put y somewhere twice. So if we want to reward with a factor of y for every plus spin, so each time when we get a plus spin, and plus spin is when we get something at the top of a vector, we should reward by y. So what gives us the top of the vector? The top of the vector we get by multiplying, well essentially we get the top of the vector by multiplying the first line. So we need the first line to be multiplied by y, and this is the matrix which corresponds to Ising model in a magnetic field. So essentially in dimension 1 it's very easy to analyze, because whatever happens, magnetic field or not, different temperatures x, it's just diagonalizing a matrix 2 by 2, which every student can do. So this is well an easy exercise to see what happens with this matrix and whether it is any different. Okay, so that was the Ising thesis, and that's how he got his name immortalized with thousands and thousands of papers. If you Google Scholar it, there will be more than 10,000 of papers with Ising in the title. He had a not a very easy fate, because he was half Jewish and he was working in Germany, and he managed to escape in time to Holland and Denmark, but then there he had to hide from Germans. Eventually he migrated to the United States and he abandoned working in academia. He taught in a college, and by accident in the 50s he learned that his model became famous, but he was just teaching physics at a college. What he did in his thesis, he left a remark that his argument works not only in dimension 1, but also in dimension 2 and 3. And so in dimension 2 and 3, in this model, there is no phase transition, so it's not a good model for magnetism. And his thesis was widely circulated, so many physicists read it, essentially all physicists of the age have read it, and proposed different models for magnetism. So, for example, all three I mentioned, Pauli, Heisenberg, and Dirac, they proposed different models for magnetism, not just following the remark of this PhD student, which was erroneously made. So, for example, another famous model is XY model of Heisenberg. It's just the same model, but instead of plus minus spin, you have spins which can point in any direction. And then the force of interaction between two nearby atoms is exponent of a scalar product of these spins. So people usually credit a letter of Einstein, or rather letter of Seward signed by Einstein to American president for studying Manhattan Project. But that letter contained the back of an envelope calculation for the critical mass of needed for atomic bomb, and the back of envelope calculation was 5 tons. So they mused in there later that you should build a ship carrying this nuclear bomb, which would weigh like 15 tons, and the ship would sail into the port of Hamburg and blow Germany to smithereens. So it was already at the onset of the Second World War. And then pilots did with Otto Frisch a similar calculation, only they got a more correct answer, about 5 kilos, and they sent it to British government, and that eventually was transmitted to American government and started Manhattan Project. But he did a lot of very important theoretical work as well. And one of the things he did, he observed that actually in dimension 2 the Lenz-Ising model undergoes a phase transition. So it's actually a correct model for magnetism, or at least it exhibits the phase transition. So here's his argument. So we try to do the same thing, not for one dimension, but dimension 2. So we take a square. So here is a square 11 times 9. So we take some rectangle or square, and we assume that it magnetizes the boundary, though all boundary is red. And for a given temperature of x, we want to calculate what is the probability that the center is red or the center is blue. So the first question is, does the method of Ising work? So method of Ising would be take 1 plus x to the power number of edges of this square. Does this method work or not? So this is a question, so to keep everyone sharp and awake. Can you write that partition function is 1 plus x to the power number of edges? So if we open up this binomial, so how many edges are there? So there are basically, so for n, 2n by 2n squared, there are basically 8n squared edges. So you have binomial 2 to the power 8n squared. But how many configurations we have? 2 to the power 4n squared. So if we open this binomial, we get something extra. Why we get something extra? Because, for example, if you go around some loop and you start from red spin, you always return to a red spin. So the length of a loop, you always have even number of flips. And this stupid binomial doesn't account for that. It just gives you all the possible terms. So this doesn't work. Okay. Does the other method of Ising work with what is now called transfer matrix? Well, suppose we want to move left from right, from left to right. Then what we do, we cut our model, well, about here, and we start just moving, multiplying by a matrix. But before, why we had matrix 2 by 2? Because we cut our rod at one spin, there were 2 possible states. Now if I cut it here, there are 9 spins. So if there are 9 spins, there are 2 to the power 9 possible states, 512. So I will have, for this picture alone, I will have a matrix 512 by 512, which is already much more difficult to linearize. And I will need to linearize it for arbitrary large n. So it turns out that it is possible to linearize this matrix. That was eventually done by Rodney Baxter, and that's relates very much. It relates to star triangle and Young-Baxter relations and to very complicated physics from quantum field theory. But it's possible to do, but it's very complicated. And it's not possible to do in dimension 3, so it's purely two-dimensional thing. And this is the first thing where we see when dimension 2 is different from dimension 3. But that will come later. Now, how Pyros calculated this, and Pyros' argument are like Ising works in 2 and 3 both. So what Pyros did, he tried to compute z minus and z plus, or rather compare them term-wise. So suppose we have configuration from z minus, where the spin in the middle is blue. So let's look at what is called domain walls. Those are boundaries between red and blue. So you can assume that red is a continent which has blue seas inside, which have red islands inside, which have blue lakes inside, and so on and so on. And the boundaries are called domain walls, so those are rather shores of the lakes. So if middle is blue, it's surrounded at least by one domain wall. Actually, it will be surrounded by odd number of domain walls. So in this picture it's 1, but it might be 7 or 9. So let's take the smallest one, so it has this shape, and let's flip the cover inside it. And let's compare the weights of these two pictures. So the two pictures are essentially the same, except for this domain wall in the middle. So the only change in weight we did, we changed along this domain wall. So here we have So there is this red-blue pair which we have on the left and not on the right. This one, this one, this one, this one, this one. So on this picture the perimeter of this wall is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are 12 edges which separate red from blue, which disappeared when we move to the right. So the weights of those two, they are different by x to the power 12, or in general by x to the power L, where L is length of this loop. So we already are almost there, because we have shown that for every configuration where blue is the center, there is a configuration which can be paired with it, where red is in the center. And the weight of the left configuration is much smaller, because x is smaller than 1. So it's x to some power, usually a large one. We get that probability of left configuration. So is this enough? Is this enough? Well, this is not enough. So the question is, why is this is not enough? Well, the main reason why this is not enough is that there are different left configurations which get mapped to the same configuration on the right. So for example, I could have taken a very small loop of length 4 and flipped it to blue inside it. So I have a different thing on the left which is mapped to the same on the right. So for example, this thing on the right, you get it from several configurations on the black, about, well, I don't know, 40 or so, and some of their weights actually is quite large. So it doesn't immediately have. But there is a very simple observation with lots of overkill which we get here. The probability of the left configuration is smaller than x to the power L probability of right when we normalize. So in particular it's smaller than x to the power L. So probability of this configuration is smaller than x to the power L, where L is the length of the loop. And let's now evaluate how many loops of length L we can possibly have. So this is a very stupid and straightforward estimate for the number of loops of length L. We start somewhere at a distance no more than L over 2, because we have to have a loop around of length L. And we walk L steps, and each step goes either straight or left or right. So at each step there are 3 choices. So make L steps, 3 choices, 3 to the power L number of choices, and we start from L over 2 possible points. So probability of having minus is less than x to the power L, probability of a given configuration, times the number of ways to choose this loop, 3 to the power L, L over 2. And we have to sum only for even L, starting with 4, because loops are always of even length, and length at least 4. So this is a geometric progression. If x is small enough, it sums to small enough number. Now we have L in front. It's again a trick which teach you in high school or first undergraduate year. So basically it's sum of sums of geometric progression. So here I did the summation, it's the exact formula. And what you get x in the denominator and 1 minus x in the numerator. Well, x in the numerator and 1 minus x in the denominator. So when x is small enough, the denominator is not really important, it will be close to 1. On the other hand, the numerator will be very small. So in this particular case, if x is smaller than 1 over 6, you can check that this is small 1 over 9. So what Pyros proved, and what we have proved up to now, that if temperature is small, x is smaller than 1 over 6, probability of C to C minus in the middle is at most 1 over 9. No matter how large our domain is. Even if it's 1 billion by 1 billion, still the information from the boundary propagates to the very center. On the other hand, if x is equal to 1, all configurations are equally likely. So information doesn't propagate. And this proves that there is a phase transition which happens somewhere between 1 over 6 and 1 over, between x 1 over 6 and x equal to 1. Now, what do I mean by phase transition? I mean that when x is equal to 1, you get this configuration which totally disorders. When x is very small, you tend to minimize the power of the number of red-blue pairings. So, for example, if your boundary is all red, you would get a picture like the bottom of this picture. Here I put the so-called Dobrushin boundary conditions, red below equator, blue above. So I'm forced to have this interface, and we have this interface which very little deviates from a straight line and very small lines. So what is interesting is that you don't have a continuous spectrum of behaviors. all numbers smaller than Curie temperature, they exhibit this behavior if box is large enough. All numbers larger than Curie temperature, they exhibit this behavior if box is large enough. And exactly at Curie point, there is a separate behavior which is neither frozen, neither chaotic. It's also chaotic, but with more structure. So, and this is what you expect in any physical system of this type, that there is a Curie temperature. For low temperature, it's a frozen state, like ice. For high temperature, it's chaotic state, like water. And at 0 degrees, it's water ice. It's kind of this mesh of, so it's sort of kind of strange sludgy thing, which is also chaotic. And this is essentially what Pyros proved. He proved that there is a critical temperature, and then that eventually led to an avalanche of different other works. So the first work was by Kramers and Vanier, which came almost immediately after, and was the first, so it was already the Second World War ranging, and maybe the last transatlantic collaboration before 1945. So they actually calculated the critical dimension, critical temperature in dimension 2. So it became clear at that moment that there is something special with dimension 2. And I will speak maybe a little bit more about it later, but essentially the situation is like that dimensions 2, 3, 4, they are the same qualitatively. You have a critical temperature, you have phase transition, but in dimension 3 we cannot calculate it, some transcendental number. And in dimension 2 we can calculate it exactly. And even more so, so that I can also prove this argument, but maybe we'll just skip to more modern things. It's a very nice combinatorial argument which exploits duality between Ising model at temperature x and Ising model on dual lattice at temperature y, when x and y are related by quadratic relation, and it has one fixed point, this quadratic relation, so this gives us the critical temperature. And but the shocking thing came in 1944, and not from a physicist or mathematician, but from a chemist, Lars von Zagier, famous for his reciprocity law and Nobel Prize for that. So he wrote a series of papers, some with Breuer-Kaufmann, and also Breuer-Kaufmann wrote a paper alone, where they actually calculated partition function for a square, its asymptotics, and they calculated many other things, and it became an avalanche of results. So basically the bottom line is that two-dimensional Ising model is exactly solvable. So what does it mean? It means that there are many arguments, not always rigorous, exactly solvable doesn't mean rigorously solvable, which give you exact values for different physical quantities like temperature of phase transition, like behavior of magnetization. And it's a bit of a miracle because when you have a phase transition, you don't get an analytic function, you have a function with a jump. And normally, when you write formulas, you write analytic formulas. But the limit of analytic formulas can give you a non-analytic function. And it's a miracle that you can do this. And eventually it became also very applied to other phenomena in physics, and even economics and biology and computer science. So I don't have time to speak about all of this. I'll just mention two developments and their result. One development is a renormalization group for which is not a mathematical object yet, but for which Ken Wilson got a Nobel Prize in physics. And essentially what you do, you forget some degrees of freedom. So for example, there is box spin renormalization. So usually people use space renormalization, but it's more geometric. So what you do, you split your model in a square, say 4 by 4, which are voting districts, and each block of 16 spins elects a representative by majority vote. And then you get an Ising model on a new lattice with a new mesh, so we change the mesh of the lattice. And it turns out there is Kant-Waving argument which says that if you change appropriately the temperature, you get the same behavior. So there is this map which changes the step of the lattice and the temperature. And how you envision it, that there is a big space of all the Ising models, all possible lattices, all possible meshes, all possible temperatures. And then there is this renormalization transformation, or rather a group of such transformation, because you can do 4 by 4, but you can also do 7 by 7, or there are other renormalizations. And it's a very much very big dynamical system in an infinitely dimensional space, but it behaves like the usual dynamical systems we see in this school. What you expect is that Curie point arises as a fixed point of this dynamical system. So the frozen regime is a fixed point somewhere in the boundary, which is trivial, just everything is sucked in. And Curie point is this sort of unstable point, so there are attracting directions, there are repelling directions. And this is why it's very hard to observe in nature, because mostly what happens that you get attracted to it, but then you speed off on some hyperbolic trajectory. So this is the vision. The vision is perfectly correct, but we not only don't know how to prove it, we even don't know how to define rigorously the space of all the Ising models so that this makes sense. And probably it's a project for another at least 5 years, so it's hence 2020 in the title of the talk. Now I have 2 more minutes, we started a bit late, so these are last 2 slides. So this is how renormalization looks in 2D Ising. So there is a frozen point and everything below critical temperature normalized to it. There is chaotic point and everything above critical temperature attracts to it. And there is a repelling point, which is exactly this thing. Now the next thing which happened is that if you believe that this Curie point is unique and it's so important, it will be invariant under rotations and translations and shrinking. For example, shrinking by 4 invariance comes because you have this block spin renormalization. And we know that conformal transformations are those transformations which locally are translations, rotations, and rescaling. And then Polyakov with Belavin and Zamochik made this leap of faith. They said that if Curie point is invariant on translation, rotation, and rescaling, it should be transparent at the all conformal maps. But in dimension 2, unlike in dimension 3, there is an infinite number of conformal maps, because any bounded simply connected region can be mapped to any other. So Curie point has infinite number of symmetries. If something has infinite number of symmetries, it's a very special object. And it allowed Belavin, Polyakov, Zamochik, when the others starting with Curry, to make lots of predictions. So this is an example of a prediction for an Ising model at infinite temperature, which is called percolation. So I tossed a coin for every hexagon here. And then I can't really speak about magnetization because every hexagon is equally likely to be white or yellow, but I can ask whether the water will seep through white holes. So here it goes through white holes. Now, does it go on this picture? So this is like an oculist exam. Actually, the correct question is why it is so difficult to see whether it goes. Oh, no, that's not. Okay, so I asked computer to color it in blue, the path if you put water on top, and it's a rather fractal set, and these are 2 predictions from physicists. One is the dimension of this cluster is 91 over 48. It means that if I take box million by million, this cluster will have million to the power 91 over 48 points. And the path has dimension 4/3. So if I take cluster million by million, million to the power 4/3, how much is million to the power 4/3? Million to the power 4/3, well, okay, 1,000 to the power 4/3. How much is 1,000 to the power 4/3? 10,000. And million is 100 million. So if you have 1,000 by 1,000 box, then the path will have length 10,000. So it will be 10 times bigger than the box, so it will be winding and it will be fractally difficult to see. And Karti got a formula to how to calculate this. So this is where maybe I'll stop, and then after the break I'll speak about the mathematical development. So that's time for a break. In mathematical language, a random distribution. So not a random function, but a random distribution. And distribution is already a complicated object. Random distribution is a very complicated object. And Shamlov revolution is a more down to earth. It's a more geometric, geometric description of the Curie point. And the other thing, we have here conformal invariance, as we indeed have it, and it was predicted by Polyakov, Belavin, and Zamochik. And we observe discrete manifestations of conformal invariance. We observe some discrete analytic functions, observe discrete conformal structure. Now, how it relates to what physicists did? Well, first, maybe the most important thing is not that we give rigorous proofs of the things they predicted, but it's a new approach which also brings some new physical intuition. So there is a cross-fertilization with conformal field theory, and it gives new results. So the main thing is that it's a new approach. We still haven't managed to rigorously formalize what physicists did before us, but we managed to invent different approach, which is also useful in physics. So I gave two proofs, old proofs and combinatorial ones in the first part of the talk. So now I will try to give a glimpse of two new objects and how they work. And the first is the Schramm-Loebner evolution. So it's a way to construct random conformally invariant fractal sets, and it was introduced 15 years ago by that Schramm, who was really outstanding Israeli probabilist who worked first in Israel in Weizmann and then in Microsoft Research in the United States. Unfortunately, he died in a hiking accident very young. And SLE, so Schramm-Loebner evolution, is a one-parameter family of random curves which essentially describe all scaling limits of domain walls. So, for example, for percolation, the domain wall here it's rather complicated. As I said, it has dimension, so this curve is domain wall, it has dimension 7/4. So it's SLE 6, and it's a theorem that converges. There is another model, it's called uniform spanning tree, where domain wall is space filling, and it's actually, we cannot see it on this projector, but it's a random piano curve. It's described by SLE 8. But there are, I will see less fractal examples for it. So here there are two fractal examples. This is a fractal curve of dimension 2 space filling. This is a fractal curve of dimension 7/4. Now, this is his reasoning. So this is a slide from his first talk on SLE. So what he the question he tried to ask is the following, that we have this percolation picture. We want to study whether there is a wide connection from top to bottom. But even if we prove that there is a wide connection and we calculate its probability, it's not enough to get the whole picture. So let's better study whole picture. But whole picture is too complicated. What can be scaling limit? Covering of a plane in two colors? Well, what kind of covering? Measurable covering or something? It's a complicated question, and it actually took us another 10 years to solve this question. So now we have an answer. But he suggested to first solve an intermediate question and to study the domain wall. So what happens on this picture is that we study with half plane or maybe any other domain, and we take the Gaussian boundary condition. One half of boundary is gray, one half of boundary is white. And we put here a small insect, say an ant, who starts walking using left-hand rule along the gray cluster. So we get this red curve. So it's a random curve on the lattice. Suppose that we believe physicists. Physicists say us that this model is in the scaling limit when mesh of the lattice is very small, when we watch this half plane from the very, very end of the room, is conformally invariant. So this random curve, if mesh of the lattice is set to 0, tends to a random conformally invariant curve. Now, if we have some conformal invariance involved, how we describe a curve? Fortunately, there is a method which was invented long before, and it's called Loebner evolution after Karl Loebner, and it was invented to solve Bieberbach's conjecture. So Bieberbach's conjecture wasn't solved by Loebner, it was solved by Louis de Branche some 60 years later, and this solution killed much of the interest in half of complex analysis in the theory of conformal maps, because there it was like a beacon, like a lighthouse problem which everyone tried to solve, and then when something like Poincaré conjecture this goes, then people lose interest. So the conjecture, it stated that if you have a map of a unit disk into the plane and you expand it to the center, then nth coefficient is no more than n. Well, you have to normalize it, a1 is equal to 1, then nth coefficient is no more than n. So what Loebner did, he started studying maps of a disk to a disk minus a slit. Because essentially any domain you can write as a disk minus a slit. Just if you have a very big domain, take a disk which is yet bigger and then draw a slit around the domain and you get a disk with a slit. So his method tells you how, when you progressively draw the slit, coefficients of this map change. So this is still used in quantum theory. It's actually used by actual people who are building robots. And it eventually, after 60 years, gave solution of Bieberbach conjecture, but the counterpart conjecture were the same as asked not for any map, but map for a bounded map. What would be the best estimate n to the power gamma, what is the value of gamma, is still wide open. And the reason is that for Bieberbach's conjecture, the extremal map is a map of a disk to a plane with half line removed. And in this case, it's a plane with some fractal removed, and we don't know which fractal. So what is the linear evolution? So let's try to invent it, like Schramm actually reinvented it and then discovered that he already heard about it in graded course, just forgot. So suppose we want to describe this slit, which in our case is a random slit, which came from percolation, but for the moment forgot that it is random. Just draw a slit. Suppose we want to describe. So let's stop the slit at some increment. Since we deal with conformal geometry, the good way is to stop it at epsilon capacity increments. So we put observer at infinity, which measures electrostatic capacity of the slit, and each time it hits epsilon, we cut it. Now, so this stops. Now we open it up by conformal map J epsilon. So this slit is opened up, so the red part is opened up, and the part above is moved. Then we open up the yellow-orange part, and the blue part is moved. Then we open the blue part. So we get this three conformal map: G, red J epsilon, yellow J epsilon, and blue J epsilon. So is it clear so far? So we just open up the bottom, then the next part, then the next part. So there are three successive conformal maps. And then we'll split into 6, then we'll split into 10, the same thing, we'll just split more and more. And any simply connected domain can be mapped to half plane. And we have 3 parameters to fix. So we can fix 3 parameters so that infinity goes to infinity, derivative at infinity is 1, and that the 0 is preserved. So the first two, they fix how these things start. Then normally you would have a sum of negative powers of z, and normally I would put coefficients, so this coefficient is fixed at infinity. Normally I would put here coefficients a0, a minus 1, a minus 2, and so on and so on. But I didn't, because these two coefficients, they play a very special role. So this coefficient is exactly electrostatic capacity. So in complex analysis course, if you discuss a bit relation to electricity, then you will see that this is exactly electrostatic capacity, this number. So actually it's not epsilon capacity increment, but 2 epsilon capacity increment. And this will play a very special role, so I denoted it by W epsilon, not by AZ. Now, what we get, the G and epsilon, will be composition of these maps: red J epsilon, green J epsilon, and blue J epsilon. And if we believe physicists, because we have conformal invariance, these maps, they will all look exactly the same, because we have a random conformally invariant curve. We took this thing out, but this is again the same conformally invariant curve. We took this out, again the same conformally invariant curve. So we have 3 independent maps which have exactly the same distribution. So they are independent, identically distributed maps. So G and epsilon will be composition of 3 copies of n copies of J epsilon, which are like that and identically distributed independent. Now an exercise in formal power series. Compose n maps like this. The main term will be z. This coefficient will be additive, so we'll get it from each of these maps, and each of them will be W epsilon. And this coefficient is also additive. Next coefficients, they are already not additive, they are very quadratic and complicated, but the first two coefficients are additive. It's because they are with power 0 and minus 1, and the first number is z. So essentially what you get is that if you write J and epsilon like this, it's a decomposition of things like that. So W and epsilon, this coefficient, the time and epsilon, is a sum of n independent coefficients W epsilon. So this coefficient as a random number, because we have a random map, then a random coefficient, it behaves like a Brownian motion. You can split it into n independent, identically distributed parts. So it's basically a theorem that if you have a random variable, which you can infinitely split into independent, identically distributed parts, and if this random variable changes continuously with this index n, with this index epsilon, it has to be a Brownian motion. So essentially we proved that this coefficient changes like a Brownian motion. So essentially what we get by performing this SLE thing for percolation, we get a random walk on the modular space. The modular space here is trivial. It's just a disk where I fixed a half plane where I fixed 0, I fixed infinity, and fixed the element of matrix at infinity. but I can try to do the same thing on a Riemann surface, then there will be non-trivial modular space, there will be non-trivial random walk. Now, of course, you can ask a question. Look, it's quite clear that if you draw a curve, you can get these coefficients. But are they enough to reconstruct the curve? It doesn't seem very logical. But actually, it's if you think a little bit, it's logical that they are enough. Because what happens when you draw this curve? You draw it with a constant speed in conformal metric. So it's like driving a car with 2 hyperbolic miles per hour. And omega epsilon, W epsilon, tells you how you tilt the steering wheel. So if you press the accelerator pedal and drive with a constant speed, if you know how you tilt the steering wheel, you will reconstruct your trajectory. But it's not easy because you have to integrate this equation. So this is the Loeffler theorem. And the Loeffler theorem basically, let me see, I did not put it. So this is the Loeffler theorem. It says that there is this equation which is very easy, but it's very difficult to integrate because it's non-linear. And this is the equation for GT, so this is the limit of what we had on previous slide. Here is a proof if you are interested. So the map GT at time t, which is opening our slit up to time t, satisfies this differential equation. And if you know WT, one parameter, you can solve this equation and get GT. And now, if we believe physicists, that scaling limits are conformally invariant, whenever you have domain O in some model, you should get here a Brownian motion. So Loeffler evolution is solving this equation. Schramm-Loeffler evolution is solving this random equation, where this is a Brownian motion with some parameter which is speed kappa. Now you can ask, well, we know Brownian motion is scale invariant, you change speed, it's the same curve. No, because we fix the speed 2 in hyperbolic metric. So we fix speed how we go. Now if I change the speed how I steer the steering wheel, the faster I steer, the wiggly is the curve. So if kappa is large, the curve is very wiggly. If kappa is 0, I am just driving in a straight line along hyperbolic geodesic. So basically, this is a parameter because the parameter is ratio of kappa to this number 2. And it's an object interesting in itself. You could write papers about it, and people have written many papers. For example, Schramm and Rode have proved that there are phases of a SLE. If kappa is smaller than 4, almost surely you get a random fractal curve which is simple. If kappa is between 4 and 8, you almost surely get a curve which touches itself, never crossing through. If kappa is bigger than 8, you almost surely get a space-filling curve. A bit less true is the theorem of Buffard, that for kappa smaller than 8, Hausdorff dimension of this curve is 1 plus kappa over 8. So for example, for 4, dimension is 1 plus 4 over 8, 3 halves. And for kappa bigger than 8, it's dimension 2 because it's space-filling. And yet less trivial is that there is duality between these two regimes, that this curve looks like the boundary of that curve. There is this theorem of Dapin-Jean and Julien Dubedin. But the main thing is a beautiful lemma of Schramm, which essentially I proved on one slide. It's the whole proof of this lemma. You need only to do it more rigorous, which says that if a domain O in some model has a conformally invariant scaling limit, it is a SLE kappa for some kappa. Now, how these theorems are possible and why this is good? Because look, we had some randomness all over the plane. But now we reduce everything to random walk, everything to Brownian motion. We're just driving the car and steering the wheel by a Brownian motion. So all the randomness is pumped into the usual Brownian motion. So all problems are reduced to problems of stochastic calculus. So if you ever get to teach financial mathematics course, and people who do analysis of probability often get to teach it, then you solve the problems which are formulated like that. That there is a stock market, there are these options which are described by this Brownian motion with drift. What is the probability that within 10 years the price of oil will hit $100 a barrel? And essentially solve exactly the equations which you need to solve to prove this theorem. So it's a statement about Brownian motion with drift which tells you what is the probability that it hits. Because how do you determine Hausdorff dimension of something? You pick a point at random and you ask what is the probability that our curve moves within epsilon of this point. Now you rewrite it in terms of Loeffler evolution, and essentially it's a question what is the probability that the trajectory of this point hits within epsilon of the real line. So it's basically a question about Brownian motion. What is the probability that its trajectory does something? And this is what people, so it's stochastic calculus, people know very well how to do. So this is, well, this is again the lemma of Schramm, which is essentially says that relation to lattice model, that if you have conformal invariance and some other property which you have automatically, then you have this relation. But the important thing is indeed we reduced everything to Brownian motion, and this allows this calculation. Now, this since then has very much advanced, so people learn not how to draw one curve, but how to draw several curves simultaneously, or how to draw simultaneously like at all points, or how to do it in a random metric, and it's still developing very fast. But the point which I like most is this really down-to-earth lemma, which says that you pick any lattice model, you pick a domain volume, and you assume that it has a scaling limit, and physicists are correct, it's conformal invariant. Then it has to be one of SLEs with some kappa. And then already if you guess kappa, you can calculate the numbers. So this is about random walk on the space of model, because you can do this on a Riemann surface, then it will be random walk in the model space. But now, how you prove these theorems? How you actually prove that percolation indeed converges to SLA6? You need to define, you need to observe some complex analysis on the discrete structure, and as I said, people often say that these two-dimensional models are exactly solvable or integrable. So integrable, it's analog with the integrability in differential equations, but it's maybe a bit of a misnomer. It's better to say exactly solvable, that there are enough symmetries that allow you to deduce something. And there are several ways to do it. So I mentioned, for example, the transfer matrix of Baxter, where you cut by a line and move from left to right, and then use symmetries to diagonalize the matrix. So discrete complex analysis is essentially a new way to look at these symmetries. So what we do, we pick a model, say the Ising model, and we find an object in this model which is a discrete harmonic or discrete analytic function. I will say a little bit later what does it mean, discrete analytic. But discrete harmonic functions, most people have seen it, just function on a graph which has the mean value property. At every vertex is the mean, its value at every vertex is the mean of the neighbors. So they are widely studied. Suppose we have such a function which solves some boundary value problems. But then in the scaling limit, this function will solve the same boundary value problem for a usual holomorphic analytic, as a usual holomorphic analytic function. And what one can conclude that our function has a conformal invariant scaling limit, because harmonic analytic functions are conformally invariant. Also, from this you can deduce that they converge, the domain walls converge to Schramm's SLEs, because you get enough information to deduce how you steer the steering wheel. And you can then calculate the best expert either with SLE or also without. So I will maybe say first a little bit about discrete holomorphic functions. First, if we speak about discretization of complex analysis, we need three things. First, we need planar graph, which will stand it for the complex plane or for some Riemann surface. But also we need it's embedded into complex plane. Why? Normally, if you want to study harmonic functions, you don't really need to embed the square lattice like this or like that. But we are interested in scaling limits, so we are really interested in the atomic structure of some material, so we need to know how they are positioned. And if they are positioned like this or like that, we'll use different definitions of Laplacian, because we want Laplacian which approximates what we see in the real space. So we need a planar graph, but also we need it embedded into complex plane. And then definition of a Laplacian or Cauchy-Riemann equations. Now, the first example of this was for harmonic function. There are many people who were involved. The most famous paper is Courant, Friedrichs, and Levy, Hans Levy. And they proved that solutions to discrete Dirichlet boundary value problem converge to the continuous solutions. So essentially, it states the following. Suppose we have some domain and a function on the boundary, and we solve a boundary value problem for Laplacian. So we find the harmonic function with these boundary value problems. But then we do it discretely. So we superimpose the lattice and find discrete harmonic function, that is function which at each vertex is mean value of 4 neighbors, which has given boundary values. So on all these edges, it has the values which are prescribed. Then we do the same with the small mesh of lattice and yet small and so on, and we pass to a limit. And then we reconstruct the continuous solution. So it's a very nicely written paper, and then it was reprinted in late 40s by IBM, because when computers came up, people needed to solve PDEs, and they realized that apparently technology was already developed. Already finite element method was put by people 20 years before on a rigorous basis. And the rigorously state that also it's related to random walk. Now, discrete holomorphic functions, they first arose indirectly in the work of Kirchhoff on electric currents. So if you have electric network, so if you present your graph as an electric network, you can put on every edge a number which is the electricity, the current flowing from one end to the other end. So it's an antisymmetric function. If current 1 flows from U to V, it's the same as -1 flowing in the opposite direction. Then in school you learn 2 Kirchhoff laws. So if there are no sources and sink, then current flowing from vertex is 0. So sum of emanating currents is 0. And then there is no perpetuum mobile, so you cannot have around some circuit a current which is continuously going around. So sum the length of the circuit is 0. On a planar graph, this is enough to check for the phases. So what Kirchhoff observed is that if you have this electricity flow, it's generated by some potential function h, and h is discrete harmonic. So essentially, discrete holomorphic function is a gradient of discrete harmonic, very much like in complex analysis, only in complex analysis you need to flip it a little bit. And Kirchhoff observed it was briefly touched upon by Den and others at the early 20th century, and then it came again to light in a paper written by 4 Cambridge undergraduate students, and the paper was on recreational mathematics. So in several journals for high school kids, a problem was posed. Actually, once it was posed by famous Russian mathematician Luzin. So he asked, is it true that square cannot be cut into squares of different sizes? So if you have a square, you can cut it into 4 squares of the same size, or 9 squares of the same size. But can you cut it into squares of where all sizes are different? And he assumed that the answer is no. Of course, for rectangles, it's fairly easy to arrive at some cutting where sizes are different. So Brooks, Smith, Stone, and Tata, while undergraduates at Trinity in Cambridge, they found a bijection between electric currents and square tilings. And essentially, this bijection is on this picture. So whenever you have a tiling of rectangle by squares, you can draw a graph where vertices of the graph correspond to horizontal intervals. So for example, this blue interval corresponds to this vertex. This red vertex corresponds to this red interval. And then if there is a square between 2 intervals, you put an h here. And the current you put is exactly the size of this square flowing from top to bottom. Is it clear, the bijection? So horizontal intervals give vertices, and edges are given by squares between two horizontal intervals. It's very easy to check 2 Kirchhoff laws. For example, why what we have at blue vertex? 28 and 5 come in, and 33 goes out. 5 plus 28 is 33. So Kirchhoff law is here. Why? Because 5 and 28 are on top, and the sum of 5 and 28 is 33 because it's the length of this interval. So hence the Kirchhoff law. Now why around for example, this face we have current 0? Because this face corresponds to a vertical interval, and it has 28 on the right, so this is 28, flowing clockwise, and counterclockwise it has 16, 7 and 5. So 16, 7 and 5 flows in this direction, 28 in the other, and they cancel out because they give the length of this interval. So it's an easy geometric B action which goes both ways. You should check some boundary conditions so that it is indeed a conformal map and there are not overlaps, so you should put something on the boundary. In general you can get functions. And what they observed that there is this bijection, but it's much easier to look for an interesting graph than for a then sit with paper and scissors and cut into squares. So eventually they find a square, and this is the smallest known example of tiling of a square by squares of different size, but they found it by just playing with graphs. That, by the way, is the most famous of them, because the first two they didn't do mathematics, the third one he was an actuary, statistician, and that he first worked on the Enigma project and did some important contributions along with Turing. And then he is really famous in combinatorics. He for a long time was a professor in Canada. Well, this is his famous theorem. Now, if we want to do discrete homomorphic functions not on an arbitrary graph but on a square lattice, there are several different definitions which work very well. For example, you can consider a function which is a gradient of a harmonic function. Then it is defined on edges. If you want to define it on vertices, there are two definitions which were produced in the same paper by Isaacs, but then forgotten and resurrected 10 years later. And one definition is that difference for every horizontal edge is equal to I times difference for nearby vertical edge. It's very much like Cauchy-Riemann equation. What Cauchy-Riemann equation tells you? Your function has a complex derivative. So derivative in this direction is I times derivatives in that direction. In discrete setting you say difference in this direction is I times difference in that direction. And there are two canonical vectors on the lattice at 90 degrees, either two sides or two diagonals. So there are these two definitions. And well, they are slightly different. So the first one is actually more adapted to a triangular lattice, and recently Dynamical and Novikov they wrote quite a series of papers about that. The second one is better for square lattice. But you can ask a question why there are no books about it. It seems to be a nice definition, and the reason is that if you want to write a complex analysis textbook, first chapter you write very easily for discrete analytic functions. You get that if two functions are discrete analytic, the sum is discrete analytic, if derivative is discrete analytic but on a different lattice, and so on, maximum principle. But once you need multiplication, you have to stop, because on a lattice product of discrete analytic functions is no longer discrete analytic. Why? Well, how do you prove that product of analytic functions is analytic? You differentiate and use formula fg derivative is derivative of f times g plus derivative of g times f. But if you do it with differences on a lattice, in second term the point where differentiate shifts, and that sort of ruins the whole magic. So essentially first chapter of a book is very easy to reproduce and makes for a very nice very nice term paper by a student. But once you hit this multiplication, it becomes very difficult, and you have to do it case on case basis depending which definition you have and what are your goals. So this is the reason why it's sort of a not a very common subject in textbooks. Now what is more common in textbooks is that it can be used to define discrete differential geometry, discrete conformal geometry. And there are several definitions. So one which is more studied is actually nonlinear definition, which leads to circle pairings. So I have shown you square tilings. Square tilings, they are related to linear definitions. So this is the square tilings which are related to linear definitions, and those are different square tilings. So by the way, people often say that square tiling would give you a conformal map, or a circle packing will give you a conformal map. But this is not quite true. Circle packing or square tiling gives you, well, let's maybe go to this picture. It gives you a conformal structure on a given graph. If you want a conformal map, you need to have two conformal structures, one from which you map and one to which you map. So if you want to have a conformal map, you need two graphs which are topologically the same and two different circle packings. For example, here is a conformal map of half disk to a full disk, and here we have chosen circle packing which is a regular hexagonal lattice, and here it got mapped to another one. Here is another example, it's an Apollonian packing, and the numbers, well, that's a good reader. What are the numbers? It's a packing of a disk of radius 1. So there are these two disks whose sum of diameters is 1, and the numbers are 2.
The last three. They sum up.
No, it's just the numbers are reciprocals of diameters. So this has diameter 1/2,
okay.
this has diameter 1/3, this has diameter 1/6. So if you do this, this is basically the modular group, and then there are very nice formula for the radii. Okay, so the discrete holomorphic functions, they've been used in statistical mechanics, well, first in paper of Kudryk, Friedrichs, and Levy. They just briefly mentioned that it relates to random walk, and more recently we used it for a number of models. So first was Ricken used for dimer model and uniform spanning tree, then came percolation, and the Ising model. So I will just, I won't give any proofs, but I'll show a few examples. So for example, there was this formula of Cardi for probability of crossing. So essentially you take some rectangular shape, you fix 4 corners, say A, B, C, D, let's move D to the corner, and then you look at the probability of crossing. So Cardi, who is a physicist, he did use this formula in the following way. He took Z on the boundary and he started moving it left and right. And he deduced a differential equation for probability of crossing. Apparently there is physical meaning to probability of crossing, but there is also physical meaning to its derivative. So his equation was essentially, if P is the probability, P prime is equal to P squared, so it's a Riccati equation, and this is the simplest equation which doesn't have a good solution. So its solution is hypergeometric function. It's a function of a modulus of our conformal modulus of our rectangle. Now what we did, we allowed this point Z to move inside. And what we look at the probability H, that there is a blue crossing which separates A and Z from B and C. So if Z moved on the boundary, it's just probability of crossing a rectangle. So this is a function, HA of Z is probability that there is a blue path which separates Z and A from B and C. And it turns out that if you define 3 functions HA, HB, and HC, they are like 3 harmonic conjugates. So they are projections, well, of course they are linearly dependent because there are 3 of them and not 2. They are like, together they give an analytic, discrete analytic function. So they are projections of discrete analytic functions on 3 roots of unity. And what we prove is that approximately they satisfy Cauchy-Riemann equations. But also for these functions we know the boundary conditions. So each of them, one of them gives 1/3 of boundary conditions. For example, HA, it vanishes on, for example, this function, what is HA vanishes on BC, or it's written on AC, it vanishes actually at BC, because if Z is here, there is no way to get underneath. But on the other hand, if Z is at A, and the lattice is very large, you almost surely will have some very small crossing which cuts it. So it's 1 here and 0 here. And between 3 of the functions, the whole boundary is covered. And then we deduce that this is the solution by playing some conformal geometry tricks. Similarly, in the Ising, we found a function which is discrete holomorphic. Now, for percolation, it's sort of a miracle. It so far worked on hexagonal lattice. For Ising, there is universality. It works essentially on any graph. The interesting thing that is the function which worked out with Dmitry Chelkak. It's not a probability of a something. It's an object which physicists call a vertex separator. So we look at partition function of this very funny picture. So look, this picture is not the usual red and blue. There is one point which is rather peculiar. There is a domain wall which ends at this point. So this point, this domain wall, it sort of separates red and blue, but when it arrives at this point, it doesn't continue. So this point is like in science fiction movies, sometimes you have this sort of loop in a space, you walk around the loop and you get to a different place. So this is a point so that if you walk around this point, your world becomes negative of your world. So black becomes white and white becomes black. And when you walk around once more, it all returns to the same space. So basically, essentially what we do Ising model on a Riemann surface of square root of Z. So there is order 2 branching point. But 2 sheets, they are negatives of each other. They are forced to be negatives of each other. And this is how this happens. So it turns out that if you calculate partition function of this model, with certain complex weight which depends on how many turns this curve made, then you get a discrete holomorphic function. You get, as a function of this point, of coordinates of this point, is discrete holomorphic. And this allows to calculate many things. For example, this allows to just tracing what happens with this function. So we fix this point and look how this function changes when we start drawing this curve. And it gives enough information about steering the wheel. It gives us a SLE3 curve, so 3 we get from this function, and it's a fractal curve of dimension 11 over 8. But also, without a SLE, we can calculate things. So this is an example theorem which physicists could not do, and we did. So we took this function with two finite points. So there are two finite points, which are these branching points. And this function is discrete analytic in both of them. Now, so you have a function g of two variables, u and v, which is discrete analytic in them, except from when you fuse them, then it blows up. So it's a Green's function of 2 points, and the boundary conditions turn out to be Riemann-Hilbert boundary conditions. Of course, if we pass to the limit, we can calculate Green's function with any boundary condition for a nice domain, so there is an exact formula. But let's go one step back before we pass to a limit. What we have in discrete setting is almost the same thing as what we will have in the limit, up to very small error, which depends on lattice mesh. But what this function gives us, if I fuse 2 points, so you see here there is a very funny curve, so there is this curve from u to v, but if u, v are one step apart, this curve goes from a point u to its neighbor. So if I add one edge, it becomes a very legitimate domain wall. So essentially this function keeps track of what is the chance that domain wall passes through a given edge. So it picks up probability that the nearby squares in this place are of different color. This is what physicists call the energy. So it's exactly what you have in the Hamiltonian expectation of a product of two nearby spins. So what physicists knew before us, that the main term is 1 over square root of 2. It sort of relates to Kramer's Vanier critical temperature. And they knew that the next term should be covariant. And if a thing is covariant and it's a function of a domain and 1 point, it can only be Poincare-metric. So it's Poincare-metric with some coefficient in front. So what we were able to do, we were able to get the coefficient in front. So if boundary conditions are all red, it's 1 over pi. If they're free, it's minus 1 over pi. And essentially what is done here is that you prove that something is discrete holomorphic. You see that it's a discrete Green's function with the Riemann-Hilbert boundary values. You write the continuous solution, and then you say the discrete is approximately the same. And then that gives you this formula. And since then this was upgraded by Chilcock, Pongler, and Isurov to all the spin and energy correlations. And when you do spin correlations, it becomes also fascinating geometric structure, because there are spin structures, spinors, and a lot of beautiful geometry. Now I have time to finish the talk, so I return to the first picture. So what does statistical physics do? It studies microscopic effects of microscopic interactions. So the current state is that there are several lattice models which we understand very well, for example, random walk. But there are many which we understand less well. For example, in Ising model we are able to do a lot. We understand perfectly that it's trivial in dimension 1, but in dimension 2 it still has many open problems. So for example, I just short to-do list what I expect will be done by 2020. So the first thing is a thing which is predicted by the Molodchikov, and he observed a very interesting thing. He observed E8 symmetry in two-dimensional Ising model. So E8 is the famous Lie group, sort of the most interesting Lie group. So here is the Dynkin diagram. And in Ising model there is no Lie symmetry. If it's on square lattice, there is symmetry of rotation by lattice and symmetry of flipping the spin, plus minus. But he observed that if you take it critical temperature and you perturb a little bit magnetic field, there are some E8 structures appear. So he is a physicist, he never rigorously proved, and even physicists don't understand this paper. But what happened is that 4 years ago, a group of people observed this in a laboratory. So what they did, they took a one-dimensional piece of string. One-dimensional piece of string is one-dimensional magnet. but if you supercool it, it exhibits quantum effects, so it becomes a quantum Ising model. So by the way, I should say that Ising model arises because of the quantum effects, but in itself it's a classical model. There are no quantum mechanics in the model itself. There is quantum version of it where spins, they flip. And if spins flip, what you can do, you can draw a time evolution. So if you have two-dimensional quantum model with flipping spins, you draw evolution, it will be a three-dimensional model with normal spins, not flipping. So it will be a graph. So there is this usual bijection that two-dimensional quantum is three-dimensional normal. So for example, one-dimensional quantum is two-dimensional normal. So in two-dimensional model, Zamolodchikov observed this E8, and physicists checked it in the lab for one-dimensional quantum supercooled string, and they saw that the first two eigenvalues, they have golden ratio as their ratio. And so they claimed that they observed it, and it would be very nice to prove. The second, there is this picture, so we analyzed completely with Chilkov this middle thing. So it's this SLE3. The left thing was before analyzed by Pfister and Velinik. They indeed proved that this thing tends to straight line, this is a frozen regime. Now, this should tend to the same picture as percolation, but that we only know at infinite temperature on hexagonal lattice. And this relates to renormalization, so just understanding this. And, well, there are also studying it on random graphs. I don't want to get into that for lack of time. But what is maybe more interesting that in 3 dimensions there are no theorems so far. Because we expect that there are no nice numbers like square root of 2, just there is same quality of behavior, and essentially there were no theorems. So the last year colleagues Michael Eisenman and Godimino Kupan Siderevich proved that in 3 dimensions, when phase transition occurs, at the point Curie point there is no magnetization. So magnetization only starts in low temperature before. So it's kind of the first step in analysis, so maybe finally mathematicians will do something for dimension 3. So it's kind of an interesting thing that we understand very well 2 dimensions because of the complex analysis kicking in and different algebraic structure. But quality with dimension 3 should be the same, and maybe now we'll be able to do. So that's probably it. Thank you for your attention.
Are there some questions?
Are there some theories that involve some continuous media of this kind, or is just only discrete?
Well, I mean, there are two things. I mean, first I would say that no media in the real world is actually continuous. We all believe in atoms nowadays. On the other hand, atoms are so much smaller that effectively you have a continuous medium. To the best of my knowledge, for example, in these problems you never see the lattice structure. We are now trying to write some Hamiltonian where you would see lattice structure on a large scale, but so far we are failing in that. On the other hand, Curie point effectively is described as a continuous model, as a quantum field theory with continuous medium, but we cannot really do it rigorously because it's a quantum field theory, which in mathematical language is a random distribution, and essentially the only random distribution we are, as mathematicians, comfortable with is Gaussian free field. It's a random distribution where correlations decay like Green's function for Laplacian. And all others, the physicists deal actually with random distributions which are not number valued but which are operator valued. And that we are not taught how to do in functional analysis course. So that's the problem, that when you deal with continuum medium you have to probably deal with very complicated objects which we mathematically are not very comfortable with.